So in this example, we have a homeowner who's connected a rain barrel to a downspout leading from the roof of their house. So here's the rain barrel, here's the downspout. Assuming the downspout channels all of the water from 500 square feet of roof area, the area when viewed from above, how long does it take to fill a 55-gallon rain barrel during a rainstorm with a constant rain accumulation of 1 inch per hour? So these are some pretty typical numbers. Now, when it says that it's channeling all the water from 500 square feet of roof area, the area when viewed from above, what it means by that is, so let's say here's a house, and the rain barrel is here, and the rain's coming down. I'll just draw it on sort of half the house. What it means is that this cross-sectional area here is the 500 square feet, and it's coming down at an accumulation here of 1 inch per hour. So what's happening is, as the rain comes down here, it all collects onto the house, and you can imagine that it goes into this downspout right here, which would then fill into the rain barrel. So let me just call it m dot in. It's m dot in into the rain barrel. So all this rain accumulating here will collect onto the house and then eventually work its way into the rain barrel and start to fill it up. So that's the idea. All right, so just with that in mind, let me go ahead and just calculate the m dot in. This is the mass flow rate going into the rain barrel. It'll be the density of water times the rate at which it's coming in. So this is, I'm going to call this h dot. The h dot is the 1 inch per hour. It's the rain accumulation coming in. And then A is the cross-sectional area. So it's like a density times a velocity times an area. So that's the density of water. This is, let me just make a note of it. This would be like 1,000 kilograms per cubic meter. We're going to assume that the water is incompressible. It's just like an incompressible liquid. This would be the 1 inch per hour. And this would be the 500 square feet of roof line. So that's the mass flow rate going into the rain barrel. Now if I draw a control volume of just the rain barrel, and then we have the m dot coming in here. Okay, and then let me go ahead and write out conservation of mass for this. This is really a conservation of mass problem because we're interested in knowing how much mass is accumulating in that rain barrel as a function of time and just ultimately how much time it takes to fill up the barrel. So we'll write out conservation of mass. So it's the time rate of change of mass in the control volume is equal to the rate at which mass is coming in minus the rate at which mass is going out. Now there's no mass going out of the rain barrel. We're assuming there are no leaks anywhere in here. The mass flow rate coming in is m dot in. That's what we just calculated right up here. Okay. And then this will tell us how the mass is changing within the rain barrel as a function of time. Okay, and by the way, I'm just going to rewrite the mass inside the rain barrel as the density of water times the time rate of change of the volume of water inside the rain barrel. So this is the density of the water. This is the time rate of change of volume inside the water. Because we know that, of course, mass is just going to be density times the volume, right? And so, and since I assume that the density is a constant, it can come outside this time derivative, and that's why the time derivative is only acting on the volume. So the time rate of change of the volume of water inside the control volume is going to be, oh, and by the way, one other thing I should mention is as the water accumulates inside this rain barrel, the mass inside the rain barrel, well, inside the control volume would include the mass of the water plus the mass of the air, right? Because there's some air inside here and then there's water. And so when I take the time rate of change, let me just say something more about this. And of course, the mass of the water will tend to be much larger than the mass in the air of the air, right? Because they have such different densities. So when I do the time rate of change in the control volume, the time rate of change really is just going to be about equal to time rate of change of mass of water in the control volume, because the mass of air doesn't really contribute very much. So that's why when I'm writing this out, this is just the density of the water times the time rate of change of the water volume. Okay, it's not. This is not meant to be the volume of the control volume. Let me go ahead and put H2O here, just to make it clear. This would be the NH2O. All right, so let's go ahead and substitute in the expression we had for the mass flow rate coming in here. So that's the density of the water times H dot times A. You can see that the densities of water cancel out, and so the time rate of change of the volume of water inside the rain barrel will just be the H dot times A. And we know the values for this. We said that that was 1 inch per hour, and this was 500 square feet. And so when you plug in the numbers for that, that'll come out to be 41.67 cubic feet per hour that's accumulating. Let's go ahead and put that in terms of gallons, since we're told we have a 55-gallon drum. So that'll be 311.69 gallons per hour. It's a lot of rain that gets accumulated here. Okay, so that's the rate of change of volume inside that 55-gallon drum. So if you want to find the amount of time it takes to fill the 55-gallon drum, let me call that capital T. That'll be the 55 gallons, it's just the volume of the drum, divided by the rate at which it's filling up, which would be the 311.69 gallons per hour. And that'll come out to be 0.176 hours, or 10.6 minutes. So this is, again, the time it takes to fill the 55-gallon drum. So here's the volume we're trying to fill. Here's the rate at which water volume is coming in, and so you can solve for the time. So it only takes just a little over 10 minutes to fill up this 55-gallon drum. So it's not really that much time, and a 500 square foot area roof is a pretty reasonable number. And a 1 inch per hour rainfall, it's a heavy rain, but it's not unusual. So I live in Indiana here, and if you look through the rain accumulation statistics for typical summer storms, you know, it's not unusual to see 1 inch per hour rainstorms. So you can fill up these 55-gallon drums pretty quickly. And in many cases, you'll see some homes with multiple 55-gallon drums, just because you can get a lot of water accumulation on the roof, and you can store quite a bit in a short period of time. All right. So this was a nice little application of conservation of mass, and we'll go ahead and end the example there.